Okay, let's look at section 8.4, property number 2. Right? So property number 2 states that let's say R is an equivalence relation on a non-empty set A. Right? So if you have a collection of all equivalence classes represented by each element in A, then this set is going to form a partition of A. Right? So if you remember from chapter 1, definition of partition is each element in that each subgroup has to be non-empty, right? So it's got to have at least one element, so for all of them, right? And also they have to be pairwise disjoint, which means that if you pick any two of these guys, they're either disjoint, which means that they don't have any common element, or they must be identical, right? So that was the second condition. And the third condition it has to satisfy is that if you take the union of all these guys together, it's going to add up exactly equal to set A. Right? So let's prove that. Right? Part A. Let's show that for all element A in A, right, this equivalence class represented by A is non-empty. Right? So let's start with arbitrary elements. So we say choose, right, any element A from this set A. Right? So this is just a given. Right? Then what we say is number 2, right? Since we're talking about the equivalence relation, so A must be related to itself by this relation, which we're using the reflexivity. So reflexivity of equivalence relation, right? Then by definition, so 3, which means that this A belongs to the equivalence class represented by itself, right? Which tells you that since we already found an element, so this is not empty, right? So we could show that for each of these guys is non-empty. So that just comes from line number 2, right? So we could just show that the first condition is satisfied. All right. Then the next one, we have to make sure that all of these guys are pairwise disjoint. All right. So let's start with 1. All right. Choose any element A and B in A. Right? So this is just a given. All right, 2. All right, so it's any element A and B. All right, so if you look at the equivalence classes, it's going to be either not disjoint, is disjoint. So intersection is equal to 0. Right, so then it's there's no problem, so we are done there. So we assume that what if this is not disjoint? So assume that right, equivalence class represented by A is not disjoint from equivalence class represented by B. Right? Right? So this is also given. right? So all it's left to show is that if they're not disjoint, we have to show that they are actually identical, all right? So 3, right? Since it's not empty, which means that there's got to be some element, so I'm going to call that element X in both equivalence class represented by A and the equivalence class represented by B, right? So that just comes from line 2, right? Right, so which means that by definition, X must be related to A. So X is related to A. At the same time, X is related to B, right? By this relation R, right? So it's kind of hard to see. So X is related to B, right? By this relation. So it just comes from line 3. All right. Then we can, if X is related to A is related back to X using symmetry. So line 5, I'll just say that A is related back to X by this relation R. Right, so this is just using number 4, line 4, and also symmetry. Right, so 6. All right, now we have A is related to X and X is related to B. So we can use the transitivity to show that A is related to B, to conclude that A is related to B. So I'm combining 4 and 5, then using transitivity. Right? Then we can use the property number 1, which we just proved, all right, in the previous video. If A is related to B, then therefore the equivalence class represented by A and equivalence class represented by B are identical. So I'm using line 6 combined with property number 1. Right? So we could show that each set is pairwise disjoint. All right. So the last condition is that if you take the union of all these guys in the partition, it's going to have to add up to A. All right. So we're going to do element chasing on this guy. All right. So line number 1. All right. We're going to choose any element, say X, in the union of all these guys. All right, so choose any element, all right, which means that 2, there must be some element A in A such that X belongs to the equivalence class represented by A. Right, so first line is of course given, right, for element chasing, and this guy it just comes from the fact number 1, line number 1. All right, then if X is in the equivalence class represented by A, but the equivalence class represented by A is a subset, so we know that let's see, so this guy is a subset of A. All right, so we know that 3 X belongs to A. All right, so I'm just using line number 2. So therefore, we know that union of all these guys is a subset of A, right? Then the other containment is just as easy. So 5, right? We're gonna choose any element, say X, from A, right? So this is given. This is just by element chasing. Element chasing. All right. So 6. All right. We know that X has to belong to. So since X is related to X itself, so I'm using reflexivity. Reflexivity. All right. So which means that X has to belong to equivalence class represented by X. All right. But this is a subset of collection of all of those guys, right? Because this is just one of them. So therefore, 8, we know that X belongs to, actually we can just say, right, X belongs to here, so which means that the A is a subset of the union of all these equivalence classes, right? And the 9, right, I'm just using line 7, and this just comes from line 6, right? And therefore, so the conclusion is union of all these equivalence classes is going to be exactly equal to the entire set A, right? So I'm using mutual containment, so 4 and 8, right? So that will verify condition that the condition number 3 is satisfied. All right, that's it. I hope that this was clear. So this basically says that if you have equivalence class, and equivalence class is going to form a partition of the original set A. All right, that's it.